Hey everyone, welcome to today's Explainer. We're taking a journey straight into the foundation of data science, and we're going to demystify the core concepts of programming and probability. And the best part? We're doing it without getting bogged down in all that heavy math. So let's jump right in and see how we can unlock these tools.
So, what is the absolute biggest barrier to data science? Well, for a lot of folks, it's this persistent, kind of scary assumption that just to open the door to data analysis, you literally need to be a master of advanced calculus. Like you're picturing yourself constantly solving these multivariable equations just to make sense of a simple data set. It's a massive roadblock, right? It stops incredibly smart people from writing even their very first line of code. But here's the secret. That roadblock, it's largely an illusion.
And that brings us to our source material for today. Statistical Practice for Data Science, with hands-on illustrations using R by Nalili, Asha, and Haim. This book is brilliant because it serves as the absolute perfect bridge into data science. Why? Well, the authors explicitly designed it so you only need a foundation in college-level algebra. It completely, 100% removes that terrifying calculus barrier. It makes the incredible power of statistical computing accessible to anyone who's just willing to roll up their sleeves and learn the tools.
Okay, here's our roadmap for this explainer. First, bridging the data gap. Then, inside your R workshop, structuring your data and the language of probability. Finally, we'll wrap up with the normal distribution and the empirical rule.
Section 1. Bridging the data gap.
Right in the text, the authors state, a key feature of this book is its minimal mathematical prerequisite, only requiring a foundation in college-level algebra. In particular, no prior calculus knowledge is required. Man, what a relief. With that massive barrier officially gone, we can focus entirely on the practical tools, the coding interface itself, and the core concepts that actually drive day-to-day data science.
Section 2. Inside your R workshop. Whenever you boot up RStudio, I want you to imagine you're walking into a craftsman's digital workshop. You're immediately greeted by 4 distinct panes. Step 1 is pane I, right up there in the top left. These are your source files. Think of this as your drafting table, where you actually write and edit your scripts. Step 2 is pane 2, the console sitting right below it. This is the engine room. You type a command, hit enter, and bam, R processes it right there and spits out the result. Then step 3 is pane 3 in the top right, your environment and history. This is basically your inventory. It lists all the data variables you've created and saved during your current session. And finally, step 4 is pane 4, down in the bottom right. That's your utility drawer. It holds your files, any generated plots, and a super handy help menu. Honestly, once you understand how these 4 panes work together, the whole workshop just feels like home.
Section 3. Structuring your data.
So now that we're standing comfortably in our workshop, we really need to understand the raw materials we're working with, right? R gives us a few different containers to hold our data, specifically matrices and data frames. Now, matrices are strict. They're two-dimensional arrays for sure, but every single piece of data inside them must be of the exact same type, like all numbers, no exceptions. Data frames, on the other hand, they are the absolute flexible workhorses of data science. They're formatted just like tables where each column can actually contain a totally different type of data. You could have one column for numeric ages and sitting right next to it, a column for text-based city names like New York or Chicago. Basically, data frames mirror the messy, mixed-up real world perfectly.
But, sometimes even a data frame just isn't quite flexible enough. And that brings us to lists. Lists take data complexity to a whole new level. They are ordered collections that can hold entirely different types of objects, of entirely different dimensions. Like, you can literally have a list that holds a single number, a vector of text, and an entire matrix, all at the exact same time. In R, heavy-duty statistical functions like linear regressions often output a vast variety of results, and R neatly packages all of that wildly varied output right into a list. It's a total game changer.
Moving on to Section 4, the language of probability.
Okay, to really manipulate these materials, we need to understand the underlying physics of our workshop, and that is probability. In statistics, random variables basically come in 2 fundamental flavors. First up, discrete random variables. These are things you can count as distinct, separate values. Think about the number of diseased trees in a forest, or the number of heads you get in a coin toss. It's 1, 2, 3. You obviously can't have 2.5 coin tosses, right? Second, we have continuous random variables. Now, these represent measurements that have infinite possible values along a real line. Think about the exact time it takes to run a mile, or a baseball player's salary down to the microscopic fraction of a cent. So the golden rule to remember here is continuous variables are measured while discrete variables are counted.
Now, for those countable discrete variables, we use something called a probability mass function, or PMF. Okay, I know, that sounds like some intense, scary math jargon. But all it really means is that we have a mathematical rule assigning a specific measure of certainty to every possible outcome. If you toss a coin, the PMF simply assigns a 50% certainty to heads and 50% to tails. The absolutely crucial rule here, and you can't forget this, is that if you add up the probabilities of all possible outcomes, they have to sum to exactly 1. Or, put in everyday terms, exactly 100%. The whole shebang.
Section 5. The normal distribution.
When we start looking at continuous variables on an infinite scale, one concept just towers above all the rest: the standard normal distribution. And this brilliantly illustrates its symmetrical, bell-shaped probability density function. In this standard version, the mean, the dead center of the data, is exactly 0. And the standard deviation, which just measures how spread out your data is exactly 1. It shows us that most of our data points cluster right around the middle, and as we move further away from that mean, the likelihood of finding a data point tails off just beautifully at both ends.
Now, another really cool way to visualize this is the cumulative distribution function, or CDF. Contrast that previous bell curve we just looked at with this smooth S-curve. While the bell curve shows you the probability at one specific point, this S-curve visually anchors how probabilities actually accumulate as you move from left to right. It starts at near 0 probability way over on the far left, and as you sweep across the possible values, the probability builds up until it smoothly caps out at 1 or 100% up at the top right.
Section 6. The empirical rule.
So why do data scientists rely on that bell curve so heavily? Well, it all comes down to the empirical rule, which is also known as the 68, 95, 99.7 rule. If your data follows a normal distribution, you know instantly that about 68% of your data will fall within just one standard deviation of the average. Expand that net out to 2 standard deviations and boom, you captured 95% of your data. Go out to 3 and you've captured 99.7% of all possible outcomes. Quantifying uncertainty with this kind of pinpoint precision, that is the true superpower of data science. It's what allows us to look at a totally chaotic world and make deeply, deeply reliable predictions.
Wow, we have covered some incredible ground in this explainer, from understanding the RStudio environment to mastering data frames, right up to the predictive power of the normal distribution. So I want to leave you with a bit of a provocative question to chew on. How might you apply this predictable bell curve to make sense of the totally unpredictable data in your own life? Whether it's analyzing your personal finances, your fitness tracking, or weird trends in your industry, the tools are now right there in your hands. So open up RStudio, load in your raw materials, and start finding those hidden patterns. Thanks so much for exploring with me today.